Now we'll be examining how to use matrices to help us solve systems of linear equations. Consider the system of linear equations. X plus y plus z equals 2, x minus y minus z equals 3, 2x plus 2y plus z equals 6. A. Write the system as an augmented matrix. B. Use the Gauss-Jordan elimination to solve the system, writing the solution as an ordered triple. So here we have the system of 3 equations and 3 variables, and we want to write the augmented matrix. So we take the coefficients of the variables and we write them. So for x, it's 1, 1, and 2. For y, it's 1, negative 1, and 2. For z, it's 1, negative 1, and 1. We draw our line, and now we write 2, 3, and 6, and there we have our augmented matrix. So in part B, we're going to take the augmented matrix and use the Gauss-Jordan method to solve this system of equations. So what we're going to do is row operations. For example, we're going to take row 2 and subtract from it row number 1. So in this case, both of the operations, we're going to leave row 1 as is. So let's write row 1. 1, 1, 1, 2. Now, row 2, subtract row 1. So it's 1 minus 1, which is 0. Negative 1 minus 1 is negative 2. Negative 1 minus 1 is negative 2. And 3 minus 2 is positive 1. Now we're going to take row 3 and subtract from it twice row 1. So 2 minus 2 times 1. So 2 minus 2 is 0. Now we're going to take 2 minus 2 times 1. So 2 minus 2, which is 0. We'll take 1 minus 2 times 1. So 1 minus 2 is minus 1. And then finally 6 minus 2 times 2, 6 minus 4, is 2. So you can already begin to see that we're creating zeros in the column of column number 1, with, of course, a 1 in the first position. Fortunately, we also began to create a 0 in column 2 in the third row. So we're well on our way to establishing our matrix that we want to get our solution. Now let's do some operations where we take row 1, which is this row, and we add to it 1/2 of row 2. And you can see that in so doing, we'll be creating some zeros in rows 2 and 3 for that, in columns 2 and 3 in row 1. So it's row 1 plus 1/2 of row 2. So 1 plus 0, 1. 1 minus 1/2 of 2, which is 1 minus 1, for 0. Same thing for this one. Now we have 2 plus 1/2 of 1. So it's 2.5, which I will write as 5/2. Another operation. We want to take row number 2 and multiply it by negative 1/2. And you'll see the reason for that is we will be creating a 1 in the position of row 2, column 2, which is exactly what we want to get 1s going across the diagonal. So, negative 1/2 of 0 is 0. Negative 1/2 of negative 2 is positive 1. We repeat that there. And now we take negative 1/2 times 1, which is negative 1/2. Also, you'll see that we have a negative 1 in this position, and we want a positive 1 there. So we're going to multiply row number 3 by negative 1. it doesn't change the zeros, it changes the 1 to positive 1 and the 2 to a negative 2. So you can see that we have the diagonal ones, or the ones going along the diagonal, which is what we want. We still need to create a 0 in this position. So to do that, we will simply take row 2 and subtract row 3. In other words, row 1 remains the same. 1, 0, 0, 5 halves. Row 2 will subtract row 3. 0 minus 0 is 0. 1 minus 0 is 1. Now 1 minus 1 is 0. Then we have negative a half minus a negative 2. Well, negative a half minus a negative 2 is really minus 1/2 plus 2. So it's 2 minus a half, or in other words, 1 1/2. We'll write that as an improper fraction, 3 halves. We don't need to change row 3, so it's 0, 0, 1, and negative 2. And now we have the matrix in the form where we can read off our solution. In this case, we're told x is 5 halves, y is 3 halves, and z is negative 2. So our ordered triple, which is our solution, is 5 halves, comma, 3 halves, comma, negative 2.